All right, welcome. Today, we're diving into a topic that goes way beyond just having a backup plan. We're going to explore how we can engineer systems that don't just survive failures, but actually become stronger because of them. I mean, just let that sink in for a second. It kind of flips everything we know on its head, right? Instead of scrambling to fix things when they break, what if every single glitch, every outage, every little shock was actually an opportunity for your system to learn, to adapt, and to get better? And let's be real, the stakes have never been higher. We count on these complex systems for literally everything: banking, shopping, healthcare. When one of them goes down, the fallout is huge and it's immediate. We're not just talking about losing money, we're talking about losing trust and damaging a reputation that took years to build. Okay, so here's our game plan. First, we'll look at why old school methods just don't cut it anymore. Then we'll get into the fun stuff, the actual engineering tools for building systems that thrive on chaos. After that, we'll see how you can spot failures before they happen. And finally, we'll talk about maybe the most critical piece of the whole puzzle: the people. You know, for the longest time, the go-to answer for reliability was just redundancy, have a backup for everything. But in the world we live in now, with systems this complex and interconnected, that's just a starting point. It's a safety net, sure, but we really need something more advanced. So look at it this way. Redundancy is all about making copies of things to handle failures you already expect. It's defensive. But antifragility? That's a whole different ballgame. It's about designing systems that actually get better when they're hit with stress and unexpected shocks. They don't just survive, they evolve. That's a massive advantage. This amazing idea comes from Nassim Nicholas Taleb. An anti-fragile system doesn't just bounce back from damage, it actually improves. It gets stronger when it's pushed around. This is the new gold standard. So the big question is, how do we actually build something like this? Okay, so how do we take this powerful idea of anti-fragility and turn it from a cool theory into something real, into code and infrastructure? Well, let's open up the engineering toolkit and see what's inside. We're going to focus on three incredibly powerful strategies. First, proactive chaos engineering, which is basically breaking things on purpose. Second, graceful degradation, which is about failing smart instead of failing hard. And third, self-healing architectures, which, well, they fix themselves. Now, chaos engineering sounds, well, chaotic, right? A little scary. But it's actually this incredibly disciplined scientific process that was famously pioneered over at Netflix. You start with a guess, a hypothesis, like, I bet we can handle this service failing. Then you carefully cause that failure in a controlled way. And then you watch and you measure everything, like how long it takes to recover, to find those hidden weak spots before your customers do. All right, next up, graceful degradation. The idea here is really intuitive. It's much better for your car to keep driving on a spare tire than for the whole engine to just blow up. So when a system is under a ton of stress, it should be smart enough to sacrifice the nice-to-have features to protect the absolutely critical ones. And here's a perfect real-world example you've probably seen. Imagine it's Black Friday, and an e-commerce site is getting slammed with traffic. A smart system might say, hey, this recommended for you feature is using a ton of resources, so it temporarily shuts that down to make absolutely sure that the most important things, searching for products and actually checking out, stay lightning fast. And finally, we have self-healing systems. Think of this like your own body. If you get a paper cut, you don't have to consciously think about healing it, your body just does it. These systems, often powered by incredible automation tools like Kubernetes, do the exact same thing. They spot a problem, like a crashed component, and they automatically restart it or move the work somewhere else, all without a person ever having to wake up and log in. Okay, so building a system that can take a punch is awesome. But what if you could see the punch coming before it even lands? That's the whole promise of observability. It's about getting such a deep understanding of your system that you can anticipate problems. And to get that kind of crystal ball, engineers have some seriously sharp tools in their arsenal. We're talking about anomaly detection to spot weird behavior, distributed tracing to follow requests through a maze of services, and AI-powered analytics to actually predict the future. So your standard alerts are great for problems you already know can happen. But anomaly detection? That's for finding the unknown unknowns. It uses AI to learn the normal rhythm of your system, its heartbeat. That way, it can immediately spot something bizarre, like a sudden flood of failed logins, and flag it for you before it turns into a total crisis. Now, this one is a total game changer for modern applications. See, apps today aren't one big program anymore. They're made of dozens, sometimes hundreds, of tiny little services all talking to each other. When things get slow, finding the culprit is a nightmare. Distributed tracing is like putting a GPS tracker on a single user's request so you can follow its entire journey and see exactly where the bottleneck is. And this is where things get really futuristic, actually predicting failures. By chewing through huge amounts of past data, AI models can learn the warning signs that show up before something breaks. It's the exact same logic airlines use with sensors on their jet engines to know when a part needs to be replaced before it fails. This is how you turn crisis response into just scheduled maintenance. We've talked a lot about tech, about code, about tools, but here's the thing. None of it matters without the right people and the right culture. At the end of the day, the most resilient systems are built by resilient teams. The technology is the tool, but the culture is the entire foundation. And it really comes down to 3 cultural cornerstones: running blameless postmortems so you can actually learn from failure, empowering your engineers to take ownership of reliability, and running game day drills to practice for when things go wrong. And this slide just nails the difference. In one world, you have the blame game. The first question is always, who messed up? The result is fear, people hiding mistakes, and guess what? The same problems happen over and over. But in a blameless culture, the question changes to what went wrong. That creates safety, encourages openness, and leads to real, lasting learning for the entire team. This simple question, which basically became the mantra for Google's Site Reliability Engineering, or SRE teams, it says it all. It's a fundamental shift from pointing fingers at people to looking for opportunities to make the system better. And look, you can't just talk about this stuff. You have to actually practice it. That's where game days come in. They're like fire drills for your tech team. You simulate a major crisis, a database going down, a network outage, and let the team practice their response in a safe environment. It builds muscle memory, so when a real crisis hits, everyone knows exactly what to do. So let's tie it all together. True modern resilience isn't just one tool or one trick. It's this powerful blend of all 3 things we talked about: engineering that embraces chaos, observability that can see into the future, and a culture that puts people first and is obsessed with learning. And that leaves us with one last big question to think about. In a world that's always changing, where you never know what's coming next, is it really enough to just be built to last? Or is the real goal, the real opportunity, to build something that's designed from the ground up to evolve?